This video covers derivatives and area under a curve. In the last video, we calculated instantaneous velocity by drawing a line tangent to the curve and getting the slope of that line. But if we don't have a graph and we only have an equation or a function that represents the motion of an object, well then we have to do something else. You could theoretically graph the function and find tangent lines to all the different points that you need to, or you can use differential calculus. In our last video, we saw that to solve for instantaneous velocity, we had to draw a tangent line to our position versus time graph curve and find the slope of that line. This is also known as taking the derivative of a graph at some point in time. Now we can do that a little bit more mathematically. On the left, we have the general form a derivative takes in your math class. On the right is the general form a derivative takes in physics. Here you have a function, which is equal to a, which in this case is just a value, a number, times x to the n power. Down here we have the derivative of your function with respect to x. So what we do is we bring down this n, whatever it is, bring it down to the front, multiply it by whatever number was already there, and then we have x, n minus 1. And then we do the exact same thing in physics. Here we're going to have a position function that varies with time, which we know from our motion graphs that time is what's changing and position changes depending on what time is. So here we have position with respect to time is equal to a, again just a value, times t to the n power. Again, these equations can get slightly more complicated, but this is the general form that you do for every single derivative. Once you take a derivative, in this case the derivative of position with respect to time, is equal to n, again we brought that n down from the exponent down to the front, times a, whatever value was already there, times t to the n minus 1. We said before that velocity is the first derivative of position with respect to time. So anytime that you start taking a derivative of a position function, what you're actually getting is a function for velocity. It's an equation for velocity. This is the standard form, the way that we'll normally see it. In class, I might do a shorthand, basically just dropping the parentheses t's. All this means is that we are taking it with respect to time, but we know that. We know that our functions vary with time, so I don't usually always write it. In this video, I will, but in class, it might be a little shorthanded. So let's try a simple function before we try these other two examples. Let's say we have a position function equal to 4t squared. What we're going to do is follow this formula. We're going to look at our exponent, bring it down to the front, so that our equation looks like the derivative of the position function with respect to time is equal to 2 times 4t. So we brought that 2 to the front, and then if we notice, we have the n minus 1, so our exponent, which is 2, minus 1. So this is what's going on. And then we can go ahead and just clean up our math. So we get 8t, and then 2 minus 1 is 1. 8 times t to the 1, or just 8t. This is our velocity function, meaning that this equation would represent the velocity time graph for the above position time graph function. Another example is a position function equal to 8t minus 3. So what we're doing is going to do the exact same equation, or the exact same formula, to each piece of the equation, starting with 8t. Here we can see that 1 is the exponent for the t, so we bring that down to the front, and our equation looks like the derivative of x with respect to t is equal to 1 times 8 times t to the 1 minus 1 power. To clean that up, that becomes 8 t to the 0, or just 8. Remember that anything to the 0 power is 1. Now we can take the derivative of the second part, that negative 3. Now, if that 8t wasn't there, then we would have a position function equal to just 3. That means that we are not moving, or that your final position is equal to 3, and that you didn't have an initial position, or an initial position was equal to 3. What that means is your velocity is equal to 0 this entire time. So when you take the derivative of a constant, it is automatically just 0. Again, in your calculus class, you go a little bit more into detail with this. For now, you're going to need to just follow it. So your final answer is simply that our velocity function is equal to 8. Now let's try these two examples, starting with the one on the right. Here, we're going to do each piece first, individually. So we see that 2 as our exponent. We bring it down to the front. That becomes 2 times 4 t to the 2 minus 1 power. Same thing over here. We have 1 as your exponent. Bring that down to the front. That becomes 1 times 2 times t to the 1 minus 1 power. And then for the last part, we have a constant, so that's plus 0. Anytime we take the derivative of a constant, it is simply 0. So to clean this up, again, this is the derivative of our position function with respect to time. Another way to say that is the instantaneous velocity function. So this becomes 8t plus 2, 8t plus 2. Now for this one on the left-hand side. Again, taking the derivative of the position function with respect to time. We look at that exponent, bring it down to the front. That gives us 3 times 12, t, 3 minus 1, always your exponent minus 1, plus, bring that down to the front, that's 2t, 2 minus 1, minus, we have that 1 as our exponent, bring it down, 1t, 1 minus 1, plus, here we have a constant, so that's 0. Here, it may not look like a constant, but we're taking the derivative with respect to t. Because there is no t here, then we can consider it a constant. So here, this is plus 0. Then we look over here, and our rules still apply, even though that this is a negative exponent. So if we have a negative 2, we bring that down to the front. That gives us negative 8. And I switch these around. T to the negative 2 minus 1. So our rules still apply. Now, just to clean this up, this becomes 36 t squared plus 2t minus 1 plus 16, again, these zeros don't count, so I'm not even going to write them, 16t to the negative 3 power. And this is our velocity function. We said that velocity was the derivative of position with respect to time. Well, we haven't talked about acceleration, and if acceleration is a change of velocity over change in time, well then if we had a velocity time graph with some velocity function, we can actually take the derivative, or a line tangent to a curve, and take the slope of that line. In that case, we would be getting the derivative of velocity with respect to time. This is also known as an acceleration. Again, this piece is going to be focused on a little bit more in your calculus class, but we will cover it again in class. If acceleration is the derivative of velocity with respect to time, and we know that the derivative of velocity, or I'm sorry, the derivative of position with respect to time is velocity, then the second derivative of position is acceleration. Meaning if we have a function of position, then we take the derivative, we have velocity. If we take another derivative, then we have acceleration. Don't worry, we'll definitely take some more time in class to get a hang of these types of derivatives. But right now, we want to redirect our attention to other information that we can get from graphs. And those other pieces of information are area under a curve. So right now, if you look at velocity versus time, and I calculate the area between the x-axis and our graph, then we can look in our units and see what we get. So let's find the area of this darker blue center. The width of this dark blue center is 2 seconds, and I'm talking about from here to here, it's 2 seconds. And the height of this dark blue center is 20 meters per second. And I'm talking about literally getting the area of this space. So, because it is a rectangle, we do base times height, meaning 20 meters per second times 2 seconds. Again, because we're talking about base times height. Here we get 40, and if I analyze my units, I'm left with meters. What that tells us is that the area between our x-axis and our graph is the displacement, how much we've been displaced from where we were originally. This doesn't give us any information about the position that we were at or the position that we ended. All it tells us is the area displaced, meaning 40 would have been our answer had we started at position 20 and gone to position 60, or had we started at position 0 and gone to position 40. All we know is that we were displaced 40 meters in this period of time. But you can also apply the same principle to find the area in these two lighter blue spaces. So I'm going to show you the area of the second part. Because it's a triangle, we're going to use 1/2 base times height. 1/2. Our base in this case is 2 seconds. And our height in this case is 20 meters per second. Again, our units work out, we get 20 meters. This doesn't mean, and I know it's a little confusing, that it looks like we've gone back to our position, but remember that we are looking at a velocity time graph instead of a position time graph. So again, we are only being displaced 20 meters here, meaning that we haven't turned around or anything, we just slowed down, but we'll talk about that example later. And the last situation would be for this non-highlighted triangle. Okay, because it is a triangle, I'm still going to use 1/2 base times height, but I want to show you that our height is below our graph. So our base, which is still 2 seconds, and our height, which is 20 meters per second here, is actually below our graph, so this is a negative 20 meters per second. So here we get a negative 20 meters. Meaning that we have been displaced 20 meters to the left of where we were. If I wanted to find the total displacement of this entire graph, I would simply have to find the displacement for each individual piece, take into consideration all the different signs, and then simply add them together.